It started as nothing, just another Martian dawn. The sky was calm, the dust thin, the world asleep beneath its pale red light. Then, in a single frame from Perseverance's panoramic camera, something moved. A pulse green. Sharp. Alive, cutting through the stillness like a breath in the void. It wasn't a reflection. It wasn't a cosmic ray. It was motion deliberate. Rhythmic. Impossible. Engineers dismissed it. Glitch. They said, but the signal came back. Frame after frame. Same position. Same frequency. Like it was trying to be seen. Within hours, the footage spread through NASA's internal network, then leaked. The internet caught fire. Mars just blinked. Someone posted, astronomers traced the light, cross-checked with orbital data, and froze. The signal lined up perfectly with one name 3. Atlas, the interstellar traveler racing past Mars. That single pulse from the Martian sky shattered the boundaries between science and wonder. It broke the internet. It broke certainty itself. For the first time, the red planet might have looked back. On Mars. Even a camera built to watch dust can change the course of science. The Perseverance rover's SkyCam, a small, wide-angle eye meant to monitor drifting clouds and shifting light, was never designed to hunt comets, let alone visitors from interstellar space. Its sensors were tuned for the color of dust, not the shimmer of cosmic ice. But on that morning, as sunlight scattered through the Martian haze, the impossible became visible. The thin air was filled with fine particles, bending light into soft halos that usually drown out anything faint. Yet somewhere within that glare, a moving point refused to vanish, too steady for dust, too slow for a meteor. When the team reviewed the frames, the pattern held. The pixels shifted exactly as an object would if it were crossing the thin daylight sky of Mars. In the static of data and dust, a story began to take shape, the first glimpse of something no one was meant to see. In a world of billion-dollar telescopes, it was a small weather camera that spotted a visitor from another star. The signal from SkyCam sparked a chain reaction. Within hours, every mission team orbiting Mars turned their sensors toward the same patch of sky. 7 spacecraft Mars Reconnaissance Orbiter, ExoMars Trace Gas Orbiter, Mars Express, Odyssey, China's Tianwen-1, and the UAE's Hope probe formed what scientists later called the Martian Network. It was a rare cosmic alignment. 7 sets of eyes, each with different abilities, capturing the same fleeting moment from different angles. High-resolution images like HIRA's aim for pinpoint detail. Spectrometers aboard Mars Express dissected the light into chemistry. Infrared sensors searched for warmth, while radar probed for density beneath the haze. For the first time, Mars was not just a planet under observation. It became the observatory itself. Data streams from 6 nations began to converge, overlapping like strands of a web stretched across an alien sky. Each sensor caught something different. A faint spectrum here, a flicker of motion there, threads of evidence waiting to be woven into meaning. For 3 hours, Mars became the best observatory in the solar system. When the European Space Agency finally released its footage, the world braced for revelation and got a whisper instead. The official GIF showed a dim, trembling, dot drifting through a sea of static. Most saw noise. A few saw gesture. Between frames of static, a breathing halo emerged, cyan and green. Alive against the Martian dust. Our AI reconstructions later revealed faint symmetry in the glow, as if the light itself was structured, not chaotic. ESA refused to enhance or over-process it. To them, truth meant restraint, every pixel sacred, untouched. In an age of viral imagery, they chose credibility over spectacle. The result, not a beautiful picture, but a trustworthy one. Then, silence. 4 days. No new data. No statements. NASA's social channels went dark. As the US government shut down, froze non-essential operations, ESA invoked its 6-month data embargo. China's Tianwen-1 and the UAE's Hope probe quietly waited for cross-validation. The public saw conspiracy, scientists saw caution. When signals are this faint, a single misread pixel can mislead the world. It wasn't a cover-up, it was a standoff between truth and interpretation. Between the hunger to reveal and the duty to verify. And for a brief moment, the world's space agencies stood united, not in silence, but in discipline. When the spectroscopic data finally arrived, the numbers didn't fit the textbooks. The ratio of carbon dioxide to water was nearly 8:1, an imbalance almost unheard of for a comet. Nickel lines flared bright, while iron remained strangely absent. The pattern pointed to nickel carbonyl, a compound known on Earth for industrial refining, but almost never found in space. It forms in carbon monoxide-rich environments and breaks apart under mild heat, releasing pure nickel atoms. Nature mimicking industry, or industry mimicking nature, no one could tell. But every scientist agreed whatever 3i Atlas was, it was rewriting chemistry itself. Light has rules. It scatters. It bends. It obeys physics until it doesn't. Observations from ExoMars and the Very Large Telescope revealed something no model could predict: extreme negative polarization. Between -2 and -4% at red wavelengths. In simple terms, the comet's dust wasn't scattering light, it was bending it back toward the source. As if the particles themselves were polished mirrors of carbon and metal, light was refusing to behave like light. It was echoing, rebounding a dance of photons that made no physical sense. Theoretical models suggested microclusters of carbon mixed with trace metals, forming fractal grains capable of backward scattering. In 3D simulations, these particles shimmered like liquid graphite under alien sunlight. Nature had written a new rulebook for light, and no one had seen it coming. The orbit of 3i Atlas refused to play by celestial norms. Its hyperbolic path sliced cleanly between Mars and Jupiter's orbits, tilted 5 degrees off the ecliptic, a near-perfect shot through the narrowest gravitational window imaginable. Statistically, the odds of a random interstellar object following that exact geometry are less than 1 in 10,000. The universe doesn't roll dice that precisely unless there's a story behind the throw. And as it swept across the solar dust, its trajectory passed near the coordinates of the 1977, signal, not proof, but poetry written in motion. The odds said impossible. The sky said otherwise. As 3i Atlas raced toward the sun, the world's instruments began to go dark. Plasma storms from solar flares flooded sensors, blinding every optical and radio telescope in the inner system. For 2 weeks, the universe draws a curtain, a radiant wall of light and heat where even data cannot pass. Whatever happens behind it, no human eye can see. Scientists call it the perihelion blackout. To storytellers, it's the pause before revelation, the breath before the universe speaks again. For 2 weeks, the world will wait, and when the light returns, so will the questions. Science, at its core, is a staircase, each step a test of what we think we know. Every anomaly must climb that ladder. From noise to meaning, the first rung is repeatability. ESA and the James Webb Space Telescope will attempt to confirm whether the same spectral fingerprints, nickel dominance, and carbon dioxide excess can be seen again under different light and distance. The second rung is multiband proof. If infrared, optical, and polarimetric data all tell the same story, the signal becomes truth, not coincidence. The third rung is dynamic geometry, the study of how the object moves after its brush with the sun. If its trajectory shifts, or its brightness behaves unnaturally, nature may not be the one in control. And the fourth, highest rung, is intent, the one no scientist dares to claim. Only if behavior shows pattern, precision, or purpose, will the question of design step from myth into data. Every anomaly must climb the ladder, one proof at a time. The blackout ends in late November 2025. From Jupiter's orbit, ESA's JUICE spacecraft will turn its MAGIS spectro-imager toward the returning comet, searching for the first glimmers of re-emergence. By March 2026, NASA's Juno will join in, scanning for outgassing jets or fragments, any sign of change since perihelion. 2 worlds, 2 vantage points, 1 mystery. The checklist is simple. Track the brightness curve, measure trajectory drift, analyze jet morphology, and compare spectral ratios nickel to iron, carbon dioxide to water. If even one of these shifts beyond the models, the universe will have spoken again. The watch window is open and the sky is waiting. Maybe it's just ice and dust, drifting through the gravity of strangers. Or maybe it's a mirror reflecting how little we truly understand. In the end, discovery is never loud. It begins with static and ends with a question. As the faint echo of the wow signal fades through the speakers, one message remains: stay on watch.